We are going to look at this system where a mass is hanging off the side, very akin to number 4 from 8.4 that hopefully you did. By the way, just a gentle reminder, of course, if you tried anything at all, extended force diagrams, wrote down stuff, whatsoever, on number 4, congrats, full credit, move on with your life. It's cool. Don't ever forget my rule in here of always struggle for 5 minutes, never more than 10. If you're making progress on a problem, cool, you keep going. And if you get stuck on a problem that says straight up challenging, you go, all right, I guess I'm not supposed to know right now. We'll work on it later. That's the goal. Moving on. So we have a cylinder and something hanging off the side. I'm going to give some numbers. We're going to say the mass of the cylinder is, I don't know, 5 kilograms. Way too freaking big for that guy right there. I think we actually measured it last hour. This guy's actually like 94 grams. 90 kilograms. A 5 kilogram object is something like 11 pounds, so we're talking a little bit smaller than the size Sally is rotating in this particular regard. It's a ridiculous number. It's meant to help with the math. The mass hanging down here, let's go ahead and call that 2 kilograms. Similarly, that is still 5 pounds. That is still a pretty heavy object to be causing that to move. We'll call this the hanging mass right down here, and we'll call this the cylinder right up here. We're going to say that the radius of this guy right here, we'll say the radius is 10 centimeters or 0.1 meters. Thinking the problem was 7.5 centimeters or 0.075 meters. This guy, so that you can see just for comparison, is in fact about 7.5 centimeters. That's where the number came from. And the question that we're going to look at here is, how much is the object going to accelerate? That is not the question that was asked in number 4. I will talk about how you get that different and what changes about number 4 as it continues. Now, let's do this real quick. Where did my other one go? Oh, no, it's back here. Sort of. The thing falling off the side. What is the max acceleration that should experience? Does it experience that max acceleration, and why? Discuss quickly with your group while I get this out. And why? Why doesn't it accelerate at its max? So again, here's the basic setup we're looking at, although this is going to be way too fast. That we're talking about right here. Here we go. Okay, so here's the setup right here. Okay, so what was the maximum acceleration that could put out? 9.8. Okay, did it put out 9.8? No. No, although it was really close in this particular case. We'll talk about why a little bit later on. And why does it not actually put out an acceleration of 9.8? Because force tension is the other direction, and you only get 9.8 if the only force acting on it is gravity. Okay, you will notice a very strong resemblance to a problem that we did earlier this year all the way back in chapter 4. It was, hey, here's an object right here, we have a pulley right here, and there is an object hanging down right there. As a matter of fact, this straight up was the lab that you did for all the way back in Newton's second law. Yes? Okay. When you did this, we would do an extended force, or sorry, just a normal force diagram. You didn't know about extended force diagrams right there. It's a force gravity of 1. You'd say force normal, and you'd call this tension. And you would call that tension up, and then you'd have force of gravity of 2 down in that particular case, and we saw objects accelerate. The major difference between that one and the one that we are working on right now is this. That one had a cylinder that was so ridiculously small, it had basically, let's say if I had to guess, 0.2% effect on what the actual answer was, nothing that we would probably notice. We are looking at here at a cylinder which is considerably sized relative to that one that we saw on the previous setup, and as such, it definitely does matter in this particular regard. Let's begin with this, okay? What is the force diagram on the hanging mass? Force gravity down, and now notice something that I just drew a force diagram and not an extended force diagram. What about that object tells me to do that? It's not rotating, or the other way to say that is we're looking directly at what about this object? Acceleration, right? So it's not rotating, so we're not looking at angular acceleration. If you look at this top guy, Okay, this top guy right over here. Okay, be careful with how I'm answering this. Okay, is the center of this going to accelerate anywhere? So what do we know about this guy's sum of forces? They are equal to 0. Correct. Now, what is this guy probably going to do? It's not going to go anywhere as far as the center. It's going to what? Rotate. So what is it going to do in terms of acceleration? Angularly accelerate. This guy is going to have an alpha. Now, I asked that question a little bit differently. I said specifically, is the center of it going to go anywhere? Because is the outside part of this going to accelerate tangentially? Yes, actually, I just knocked out my own question a second ago. What's that called? Acceleration tangential. Is the acceleration of the outside top part of this wheel equal to the acceleration that this mass hanging experiences?
Yes.
And to check that, you are right, it is yes. To check that, you just do some simple kinematics. If 3 of the kinematic variables are the same, then they all have to be the same. Yes? Does it start with the same velocity? Yes. Does it cover the same amount of displacement? The outside part of this will cover the same displacement as this. Agreed. Will it do so in the same amount of time? Which means we've got 3 kinematic variables that are the same. So that means the other 2 kinematic variables also the same. The most important of which is the acceleration of this and the acceleration of the outside part of the wheel. Cool beans? Cool beans. All right. Now, going back to this guy real quick, I'll remind you of something that we did back here to make our lives easier. Which direction will this top one accelerate? To the right. Which way will this accelerate?
Down.
To the left. Now, when we give signs to that, typically we call that one positive on top and that one negative, yes? Which is annoying given that they're supposed to have the exact same answer. So what did we do when having multiple objects to make our lives easier?
System.
We did do a system, and we said, okay, remind ourselves all the way back in kinematics, who decides which way is actually positive? We do. The standard of up is positive and right is positive is just to keep things simple and easy so you don't have to think too much about it if it's easier. In this case, it's not. So the easy thing that we did here is we said, hey, whichever way it's going, let's just call that positive. Okay? Now, in this particular system right here, you technically don't have to, okay? Because which way is this going to accelerate, this hanging mass? Down, which we typically call negative. And which way will this angularly accelerate? It'll also go negative. So you could leave it alone, arguably. I like to just leave things as positive anyway, and I think it makes it a little bit easier to understand. So what I'm going to do is I'm going to say this way is positive. Cool beans? All right. Now, we already mentioned this about the top. Since the top part of it, okay, since the top part of it is not going anywhere, we already said, we know that its sum of forces are 0, but it is going to angularly accelerate. That kind of gives me a clue into what type of force diagram should I be doing up here. Extended. So tell me some forces that belong on that top guy up there. Force of gravity, okay? And I'm going to once again put a subscript on that because there's 2 objects. That's force gravity hanging, and this will be force gravity cylinder. So what else?
Force tension.
Where does it go?
Right side down.
Okay. And by the way, how does this tension and this tension relate?
Equal.
They are equal. By the way, Haley, I thought you weren't going to be here.
Yeah, they didn't make me excuse for this
Oh,
hour.
that's late.
Yeah.
Okay. Happy to see you. All right. Next, there is another force up here. What is it, and where would it be applied? Think about it like this, if it helps. Okay. Right now, we said sum of forces have to be balanced. Yes. Are sum of forces currently balanced? No. Think of any spinning thing. What would provide your force upwards for any spinning thing, period? We'll call that the axle. Yeah, whatever's hanging in the center is going to push that cylinder which way? Up. Now, see if you can answer me this correctly. Should force normal be greater, equal, less than force of gravity cylinder here? It should be greater. Why should it be greater? Words are hard.
Gravity plus that.
Because it should be equal to both of those. As I said the other day, I don't need force normal. I'm not going to check with the ruler that it's equal to both of these together. It technically should be, but the main thing I want to see is that force normal is in fact bigger than force gravity cylinder on the case. All right. Now our goal right now, like I said, is to find acceleration. as I've got an object straight up accelerating right here, I think it makes sense just to start on that particular problem. You can start wherever the heck you want, but here's what it would look like. We're going to go sum of forces equals mass times acceleration. Yes? What are the sum of forces? Don't forget, just a minute ago, we changed the direction of positive. What are the sum of forces in this equation? Correct. And if you remember force gravity, you are always welcome now to just immediately, don't have to write force gravity, just go mg. Since that's the case for us here, I'm just going to call this mhg, or yes, force of gravity, hanging, and agreed minus tension. What mass is this? You do have to be specific when dealing with multiple objects. Mass of hanging, how come? Agreed, and I'm going to add one thing to that. It is the object accelerating, so its inertia is what we look at. All right, looking at that equation, cool. I just want to find A. What's the problem with trying to find A in that equation mathematically? Two unknowns. Now, I'll remind you, two unknowns came up earlier this chapter, and the solution to two unknowns is twofold. The easier one, which we've been doing in sum of torques, is just go find the other variable. And if you can go find the other variable by itself, cool beans, go find it and then plug it in, and then we're all set. That's not what's going to happen here. What is the second method in order to find? You have two equations with two unknowns. Correct. So, yeah. If you had to guess then, guess which one is going to have the other two unknowns? Probably the cylinder. Now, could I sum the forces in the cylinder? I mean, certainly I could. But the problem is twofold with that. If I sum the forces, it's going to equal to 0. And it's going to put two more unknowns into the situation. So now I got three unknowns. I don't want to do that. So what else might I try? Yeah, let's try to sum of torques. Now, what is sum of torques equal to now? Moment of inertia times angular acceleration is correct. Okay, now before we sum the torques or try to do anything with that, what do we have to do first? Before that, we hit place your fulcrum. And don't forget, fulcrum can go anywhere as long as it's not accelerating. So where's the only spot it can go? It has to go to the center. In this case, there's no other choices because it is circling around. It's got to go in the center, which is actually nice. I would have loved to put it there anyway, because what does that do in terms of torque? You got three forces. How many torques? One. Why aren't either of the two in the middle of these there going to be causing torque? Yeah. By the way, there technically is a force in there that would cause torque that we are ignoring. What is it? It is friction. Yes, friction is actually at a little bit of an axle pulling the opposite way. We're going to ignore friction for right now because it would cause a counter torque. But don't worry about it. All right. So that means the sum of torques is what? What is the only torque? Tension. Now, usually we would say this is what sign? Negative. But because of this, we're going to say it's positive. How you doing so far? Feeling okay to be able to repeat?
To repeat, that's the
No, well, then ask. If you don't feel you can repeat this, then please make sure you ask a question. Why did you do this? If there are any things that I'm doing that you don't understand where it came from, this is the best spot to ask. You've got to get good at asking those questions. Okay?
I don't understand why those canceled out.
Which ones?
The FG and the
torques.
T. Yeah.
Thank you. That is perfect. That's a great question, okay, because it'll help you in so many other aspects. The answer is, okay, if I were to write them up here, okay, let's just do this real quick. I'll erase it in a second. Let's go normal, okay? The way to calculate that would be the lever arm of normal times the force of normal times the sine theta of normal. You don't have to worry about all of that. All you've got to worry about is the fact is this guy right here is lever arm. And lever arm, by definition, is the distance from the fulcrum, which is here, to where the force is applied at, which is here. So what is that fulcrum? So what is that lever arm?
What do you mean?
If the fulcrum is here, and the lever arm is also here, what is the distance between those two spots? 0. And if that's 0, how much torque will normal apply?
0.
There's the reason why it cancels out. Okay, this is an excellent question. I imagine that probably even helped a few people in here as well. Please make sure you ask that. That's great. Okay, any other questions that you'd like to hit before we continue on here? So from that, what you should see is that in my picture, these two are not going to cause torque because there's no lever arm on each of them. This one will cause torque, which we'll talk about a little bit more in a second, but you can see that, yep, there is in fact a lever arm here in just a moment. Okay, I'm going to start with the right side, explaining it first because I think it's just relatively plug and chug. What is the equation for moment of inertia of a cylinder? If you don't know off the top of your head, you're welcome to look it up. 1/2, correct? 1/2 mr squared. What is this m though? Correct. I'm going to put this in parentheses, not that you have to on your work. This is just to highlight that everything inside that parentheses is your moment of inertia. If you don't want to do that to organize, that's completely fine. Do keep in mind that you always do have the option to put parentheses and brackets because like, well, I don't have to, I'm not going to do it. Yeah, but if you don't understand, it's probably going to take you 10 times longer to get through a particular problem. Let's talk about that torque. What's the individual equation for torque? Is your lever arm first? Absolutely. Now, reminder, what is the definition of lever arm? It's from the fulcrum to the force. So what is that lever arm? The radius is correct. So this is just radius, which I'm not putting a subscript on because it is straight up radius, times the force, which is tension. And what is the angle on that?
90.
You can see it right there. It is 90, so I'm going to go times 1 on that particular front. By the way, if you didn't know this about ropes coming off of things, this is a misunderstood thing by a few people. Weirdly, it's kind of cool just because of how tangential stuff. No matter which way you pull a rope, it will always pull at 90 degrees. Right? Even if I pull over here, now it's pulling off of this direction at 90 degrees. And the reason why is actually because that's what makes the most torque. Okay? So even if you pull at a wonky direction like up and to the left, you will notice that it pulls off right over here at 90 degrees. It always pulls at 90 degrees. Okay. Next. So this is, oh, I moved it in the wrong spot. My apologies. This just goes right here. Okay. Now, there is a canceling that's going to occur. I'm going to wait on that just a second. Let's look at this equation and go, all right, cool. I had two unknowns. What were my two unknowns in the previous equation? T and A, all right. Okay, how many unknowns I got here? It is 2. What are they? T and alpha, angular acceleration, correct. Okay, and that's annoying because it's not the same two variables. However, we've had this conversation already today. How does alpha, I'm going to use a different color on this so you can see its substitution. How does alpha, the angular acceleration, relate to the acceleration tangential around the outside? AT over R. I'm going to say that actually probably the easier way to have it memorized. AT is alpha times R, but yep, through algebra or memorization period, that means alpha is equal to AT divided by R. And we already said, how does that AT relate to this acceleration on the bottom down here? That conversation earlier, they are exactly the same. So what you can do now is, instead of alpha is equal to A over R. Now, I still have two unknowns, right? I still don't know T, and I still don't know A, but are these the exact same two unknowns?
Yeah.
Yes. Okay, also let's talk about simplification in this equation real quick. This is what again?
Radius.
Radius, lever arm, but yes, it's the radius. And this, by definition, is the radius. So what am I going to do probably to move this R? Divide by R, which if I divide R here, I got to divide over here, which, as somebody just said, cancels out one of the squares. Yes?
Yeah.
But also, A is divided by R, and we have an R up here. So what actually happens here? Cancels out. Do we actually need to know what radius is whatsoever?
Nope.
We do not. Switching to another color once again so I can kind of highlight. Now we are technically done with the physics part of this, and we are now headed to the math part of this. I'm going to write this equation right up here at the top in just kind of a simpler way, just kind of organize it. This says T is equal, cancel, that's a 1, so equals 1/2 mass of cylinder. Those both cancel, that canceled. So times A. Yes?
Yeah.
Yes.
I know why you got rid of the square, but why did you get rid of the other part?
Okay. So I'm going to highlight the first one even though you said you know it. This R cancels with the squared over here. Okay? When I substitute it in for alpha, this is A over R. So this R is canceling with the other one there. This would be the long way to go about it. The other way you could see that is this. If I wanted to move this R to the other side, I, of course, would multiply R, cancel that, and this would become R squared, and then you'd be left with an R squared and an R squared, and they would cancel in that particular way. Cool beans. Good question. All right. So I've got this equation, and this equation right down here I'm going to pretty much write verbatim. Mass of hanging times G minus T equals mass of hanging times A. How do you solve this?
Or plug T here.
Say that a little bit more generically because I think I'm going to do your math teachers a helpful solid and you a solid in showing you the easier way to do this system of equations. The answer is this is a system of equations. There are two methods that you have been taught to do system of equations. They are substitution and elimination, but here's my guess. My guess is after you learned elimination, you've done about 100% of system of equations with substitution from that point moving forward. Is that fair? Okay, here's where elimination is easier. One of the main reasons why students don't do elimination is 1, they don't understand it, and 2, they don't know when it actually is easier, and 3, math usually presents the problem super wonky with some extra steps in it that does not make it easier, so you'd be like, why would I ever do anything different than substitution? Let me explain very, very quickly. I'm going to take 2 or 3 minutes here to understand elimination because I think it really helps, especially moving forward in your mathematics career as well as your physics one. Here it is real quick. What does that equal sign mean? Can you be more specific than that? What does it mean numerically? They are the same on both sides, so I'm going to pick a number. They are whatever number's over here is also over here. Yes? This is exactly what you said. I'm just going to be a little bit more plain. Let's pick a number that's absolutely wrong. Let's say this side is 2 and this side is 2. They're equal. Yes?
Yeah.
Cool. We come down to this equation. It means the same thing. Now, are these equal to those?
No.
Not inherently, and more than likely, absolutely not, but they are equal to each other, right? So let's pick a number. Let's say 3 and 3. Okay? We know they're the same. Now, what elimination regularly asks you to do, which students get bothered by the most, is it says, hey, take the left sides and add to the left sides, and the right sides and add to the right sides. Well, why the heck does that work? Is 2 plus 3 plus 2 plus always going to equal 2 plus 3? So can you add all the left sides and all the right sides and them always be equal? Could you subtract 3 minus 2 and 3 minus 2 and them still be equal? 110%. So the question that you should have is, great, I see sort of how it works. Why? Why would I do it, and when does it come up? And the answer is simply both questions. In our case, is this. One of my variables right here is t. The other variable is negative t. This regularly comes up in physics for a reason that we stated earlier right over here. How are these two t's related?
Equal.
What rule tells you that?
Newton's third.
Third law, and it's a law. So is that going to happen like pretty regularly? Yes. So they're regularly going to be equal and opposite. And when you add the left sides of this equation, what are the t's then nicely always going to do? Cancel out. So the two left sides, those t's cancel out, is just this. And the two right sides are this. And the other really nice thing about this is, it just so happens that it puts all the variables on the right side where you want them anyway. Now, certainly you are welcome to use substitution. It also works. I will just tell you, it usually takes people doing substitution about 2 or 3 more lines to pull off the same trick as elimination. Elimination by far is faster and easier to do. That's why I highly suggest it. Most people don't because they're just not used to it, but get used to it because it happens all the freaking time in physics because of Newton's third law. Okay, moving on. From here, let's just find A. I've got T canceled. We don't need it anymore. I'm going to solve out the A. Don't plug numbers in yet. We're going to factor that out on the A and then do what?
Divide it.
Divide that entire quantity on the other side, so we have 1/2 mass of cylinder plus 1/2 mass of hanging. And I know you guys are still in a spot where you're like, I wanted to plug the numbers in about 7 steps ago, but here's the nice thing about what I just did. What happens now if I change mass hanging or mass cylinder in this particular case to the amount of work that you now need to do? What changes about? Do you have to redo any work here if I change mass of cylinder? That's the equation always, 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 always for this situation. And you can plug your numbers in. Of course, in this particular case, you should get 2 times 9.8 divided by, what was that, 2.5, 4.5, so a little bit under half. I'm going to guess like 4.6, 4.5 is what I got. What's the answer? By the way, here you go. Here's what I'm saying. 2 kilograms times G divided by 1.5, 5 kilograms plus, plus the, was that 2 kilograms was, yep, okay, that guy. So that's 2.5, that's 2, 4.5. 2 divided by 4.5 is obviously less than half. It's about, what do we got? It's like 4/9, something on that. So about 44-ish% of 98, it's like 4.4. I'm going to go 4.3-ish. I was wrong. All right. 4.36 meters per second squared. And to our particular point, did it accelerate at 9.8? Nope, it accelerated less than that. Will it ever accelerate more than that? You can kind of see, ooh, not here on Earth. For this situation on Earth, would it accelerate at more than 9.8? No, because you can see from the math right here that basically you got mass hanging up here and mass hanging right down there. The only way you're going to get 9.8 is if mass of cylinder is 0 or so close to 0 that we can ignore it, which is exactly what I told you was what happened in this particular case. This thing was so freaking tiny that basically it was almost 0, so we could ignore it in our system before you ever knew it was even a thing. How are we doing? Cool beans. Okay, I should be able to ask you questions like, what's going to happen to the acceleration if I increase mass hanging? And you can look at the math and be backed up on this. What should happen if you increase mass hanging? What will happen to the acceleration if you increase mass hanging? You can do this.
Acceleration will increase.
It should increase, and the reason why is, yes, of course, you have more force of gravity. You might be balanced, though, by the fact that, hey, but I also have more inertia right down here, except will that amount of increase on the bottom have the same percentage change as this guy right over here? No, which is why the overall goes up in that particular case. That being said, I guess an arguably easier question would have been this. Instead of mass hanging, what happens to your acceleration if mass spinning or mass of cylinder goes up? Decrease. Why? Okay, mathematically, agreed. So physically, why? What's that? Right, that's mathematically. I mean, like, now in terms of physics, in this situation, mass spinning up here got bigger. Why should its regular acceleration go down? You're right there, I was looking for it, but you got the general gist. Because the moment of inertia would increase. It would become harder to cause this thing to rotate by its moment of inertia increasing on that particular front. All right, now let's talk real quick about this. Going back to Cool Spainhour, I did this problem. Good news, bad news on this, guys. This is as easy as these are going to be. Okay, you need to practice. You need to practice them. I'll give you a sample problem to do for tomorrow here in just a second. But what was different about 4.4? Well, the first thing that was different about 4.4 is what Part A asked for. Part A did not ask for acceleration. It asked for angular acceleration. So let's talk about what you can do with this whole thing to find angular acceleration. Firstly, the easiest transition, although maybe not the most efficient in this, is simply this. Do everything exactly the same, because acceleration tangential, you'll notice that I dropped the tangential pretty quickly in this. Acceleration tangential and acceleration are exactly the same. What could you then very quickly do to find angular acceleration? Just take acceleration, which we just found a second ago, and divide by the radius.
I swear we did not have the radius on it.
You did, 0.075.
Oh, great.
Okay, now the other thing that you could do that was arguably more efficient, so I'm going to go back to yellow here, okay, and remind you that this originally was alpha. Oh, sorry, yellow. I said I was going to yellow. This was originally alpha. Now, if alpha is there, one of these does not cancel. So let's go back here. Pink. R squared. Nope, that's purple. Come on, dummy. R squared. One of the R's still does, yes, but this R would not. Okay. What could you do, arguably, from this position that is more efficient that would also allow you to find angular acceleration?
Never mind.
Instead of substituting alpha for A over R, what could you do?
Oh, you could get wait.
Right here, you could substitute acceleration for alpha times R in that particular front. Now, in that particular case, would the R's cancel like they did in the previous setup? It would not. There's no R in here to cancel, which kind of makes sense because like we saw a second ago, the other way to get alpha is just take this and divide by R at the very end in order to get that alpha in that particular spot. How are we feeling? Okay, let's give you guys a sample problem to start on your own. What I told last hour is, assuming that there's not a ridiculous amount of whining left in this particular class, let's see what we can do here. If you try on this and give me any sort of answer for tomorrow, depending on where it's at, you're showing decent work, I'll straight up give you bonus points on tomorrow's quiz simply by doing this. Cool, great.
I had a drink the other night.
Students, if you do this, you could learn the information more. Ugh, but it's hard. You could have bonus problems, have my left limb. Why? 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 One of them has value. The other one is a fake point system that no one freaking cares. It's fine. It's fine. It's fine. We're going to look at what's known as the Atwood machine. It's known as the Atwood machine. Okay? It is a very simple device. It is basically just this again. The only difference is now.
It looks like Mike Wazowski.
So you will notice it is just a rope pulled over the top of this, okay? And I'll give you the numbers that we are going to use. This guy, because of ease of putting it on here, is 210. Actually, I might have some
Grams?
grams, yes.
Oh,
You'll live, or you won't. And I honestly have given you the spot. I don't care anymore. All right. Here we go. Never mind, I made the numbers even easier. Okay, this is 220. This is going to be 220 grams, and the other one's going to be 200 grams. Okay. I measured this earlier in the back with the triple beam balance. This at the top is 184 grams.
What was the second one?
Okay. This was 220. This was 200.
Yes.
Okay. This is 184. Now, while those numbers do sound annoying, I agree with you. If you do it the way that I suggest, are you going to be dealing with very many of those numbers as you are actually doing the work? No. Or you can deal with the annoyance of those numbers. That's what I'm going to start to do. All of my people that love the numbers to go in earlier, I'm going to find the most annoying freaking numbers to put in these problems, pushing you in the direction of the correct way. Just do it with the variables and plug the numbers in once at the very end. What is the number to this problem? E to the second negative 2.347 end of the first. What's up? You need help with what?
What is the problem?
The problem is I've got 1 and I've got 2. You pick whichever one's which. Okay. Okay. And then I want to know what's the acceleration of this system.
The system?
Acceleration of the system.
It's also
Okay. I have told you the mass of 1, the mass of 2, and the mass of the cylinder. That is all the information I've given you. I have not told you radius.
What was the mass of the cylinder?
184 grams.
See, but I don't know how to start this.
so just
If
like,
only someone had spent, I don't know, 30 minutes showing you that and asking for questions like non-stop.
But
That would have made this easier.
You could have showed me for 30 hours. I don't know what's going
Yeah.
guys just look back
Let's
at
do
the
our diagram.
Hot dang, you do know.
Yeah, but I get confused on how many forces I'm supposed to have.
There's a never mind.
I see gravity.
All right, for those of you online, I'm going to stop this early because I'm going to check this work tomorrow. If you were looking at it today and the quiz is tomorrow, you can still do this bonus yourself. If you're looking at it in the future, I'm not going to do this again in the future. All right, see you later.